one of these. It's a highlighter. It's a highlighter pen. You know, something to mark passages or lines from your textbook or any other material, so that that area, that place, that line, that paragraphs become highlighted. You must have used it. If you have not used it, you must have seen other people using it. These are available very cheaply. I got it for around 15 Indian rupees, which is less than $1 US. Most of us know what this is. This is a highlighter, as the name suggests. Compared to this, how different is this? This is a yellow sketch pen. I borrowed it from my daughter's vast array of colored pencils, and this can also produce yellow ink. You can also mark your passages in your textbook, lines, paragraphs, etc. with this yellow pen. But what exactly is the difference between the highlighter here and the yellow sketch pen that is here? Think about it. You can pause the video a bit and then think your answer and return back, and we can discuss this. Okay? Okay. So, many of you might have thought that this one is brighter. This is a fluorescent highlighter, fluorescent marker. This is brighter and this is not. But what if I increase the intensity of the yellow paint, the yellow ink of this normal sketch pen? Will it still be as bright as this, or this is obviously going to be more brighter? This highlighter, this fluorescent marker, this fluorescent highlighter is always going to be brighter than this yellow pen. Think about it. Well, if you think that the marker, the highlighter, the fluorescent marker is always going to be brighter, then perhaps you are right. But why exactly is that? Why would the fluorescent marker always going to be brighter? Well, it's the same reason a yellow light bulb is always going to be brighter than a yellow paint. A light bulb emits light. A yellow paint reflects light. There is always going to be difference between emission and reflection. What do you ask? Well, emission is an active process. Some amount of energy is getting converted, and the light that is getting emitted is a process of energy conversion. It might be some amount of light is getting absorbed, some amount of photons are getting absorbed, and that is reconverted to a different wavelength and another sets of photon coming out, or another different phenomenon is happening. But emission is always some amount of energy is associated, some amount of energy is created, some amount of energy is converted. Reflection, on the other hand, is simply a passive phenomena. A bunch of photon goes, little bit is absorbed, little bit is transmitted, and the remaining portion is reflected. Remember the equation, 1 is equal to T plus R plus A. So, technically in reflection, no new energy or nothing actually is getting converted. It is simply the light is getting reflected, the wavefront changes its direction. That is what the basic difference between reflection and emission is. This is therefore an active device. This emits light. This, on the other hand, simply reflects light. Do me a favor, if any one of you have this marker, you must have, or you can buy it very cheaply available, just mark some pages in your textbook or any blank page, and then try to see if this glows in the dark. Do you think this will glow or this will show something without the absence of light? Think about it. Do this experiment and you will see what I am talking about. Now, imagine the exact same phenomena when it comes to microscopy. You all know what microscopes are. Okay? We take glass slides, put some amount of sample and put it under the stage. There are lenses through which we observe what is the material, what is the sample present in the glass slide in a magnified format. Now, think about reflective microscopy. Light is coming, it is hitting the sample, and then through your lens it is getting magnified and you are observing it 10 times, 20 times, 100 times magnified. Reflected microscopy. Light is getting reflected from the sample and it is getting magnified by the lens, etc. Now, instead of reflection, think about emission, where when light is hitting the sample, instead of the sample reflecting light, it is emitting light. Instead of a yellow paint, you have yellow light bulbs around. Okay? The sample starts emitting light. Which sample do you think will be brighter, will be clearer, will be more proper? Welcome to the course of Biophotonics, and today we are going to discuss about fluorescence, introduction to fluorescence precisely. Okay? Now, what exactly is this fluorescence? Fluorescence is part of this emission or luminescence, as we have discussed in previous class. Now, you all know that there are certain materials that glow, or when they are subjected to, say, ultraviolet light, they emit a specific color of wavelength, which is characteristic feature. We have seen this in numerous movies, numerous shows. You can just see them yourself. Several materials, if you have a UV light bulb, these are also available, and put some kind of salt, some kind of fluorite material under this UV light bulb, you will see that they have a distinct glow, a different glow than they were in visible light. And this happens whenever that UV light is present. If you switch off this light, if you switch off this UV light, it does not glow anymore. This entire process can very well be said as fluorescence. It might not be, there are exceptions, but for today's class, let us consider the fact that they might be fluorescence. I will tell you why it might not also be. Do you possess one of those radium watches, the watches that glows in the dark? You know, this process of phosphorescence. You shine light on it and you switch off the light completely, but you still see the material glowing. Previously, we used to have these radium watches, where if you look at your watch in the middle of the night, pitch black, you can still see it glowing. Some of the clocks also glow. So, what is the major difference between phosphorescence and fluorescence? In fluorescence, you will always need a constant supply of light. I asked you to look at the marker here in the absence of light. Tell me if you see it glow. My guess is it does not glow. That is because it is fluorescent. Fluorescent requires a constant supply of light all the time, and that light gets converted into another form of wavelength of light, another frequency, and that is what is getting emitted. You switch off the input, output gets automatically switched off. However, not in case of phosphorescence. Phosphorescence takes that light, it works with it, and it keeps on radiating that light, it keeps on emitting that light, this phosphorescence, long after the original source of light, the input, have ceased to exist, long after the light has been switched off completely. That is the fundamental difference between fluorescence and phosphorescence. Now, let us understand a little bit about the history of it and why it has been able to, this fluorescence have been able to revolutionize biology or life sciences in general for good. So, it all started with this gentleman, Sir John Frederick Herschel, in 1790 to 1871. This gentleman, British gentleman, was working on quinine. You know, quinine is present. This kind of molecule was first extracted from certain barks in Latin America, South America that is, and they help in making drugs, anti-malarial drugs. Nowadays, obviously, it has changed. Quinine is still used in tonic water. So, this gentleman, Sir Herschel, was looking at emission of water that has quinine mixed onto it, and he found out that when you are subjecting it to blue light, this solution water mixed with quinine, it gives a what he called a celestial blue emission. He reported it, but he was unable to explain it properly. But that was the beginning of certain experiment in this regard. Then came Sir George Stokes. Sir George Stokes was looking at a mineral. That time they used to call it fluorospar. These days we call it calcium fluoride, or fluoride basically, calcium with fluorine, CaF2. And he was looking at the emission of it, and he was mostly dismayed that it has a very small amount of glow. People want to have light for a longer period of time. He would say that after hitting this material with some amount of light, a different kind of light is getting reflected, or not reflected per se, is emitted. And he coined the term basically fluorescence as compared to opalescence. Previously people had opals. Opals are these this semi-precious material that emit different amounts of light and hence used in jewelry, and opalescence was a nice term previously used. Phosphorus has been discovered and phosphorus glows in dark, so phosphorus was used. So, Sir George Stokes thought that since the mineral is fluorospar, fluorite, and since it emits a light, albeit for a very, very small duration as compared to opals or any other semi-precious materials or phosphorus, let us name it fluorescence. Let me call it fluorescence. This happens to be Sir George Stokes. Another curious observation that I made is, if you look closely, Sir George Stokes' hairline look very much similar to mine. So, you do not know what I will discover in future. Yes, I could see you roll your eyes. What professor worth his salt does not want his students to roll their eyes upon his jokes. So, anyways, cut to the 19th century. This gentleman, Alexander Jablonski, born in Ukraine, Russian Federation, later joined the newly formed country of Poland, started working on the luminescence spectra of several different materials. Just read a bit about Professor Jablonski. You will find that he is a fascinating personality, a musician, above all a soldier. After joining the Polish Republic, newly formed Polish Republic, he joined the Polish militia and fought against I think Germany in World War I, got Medal of Honor, returned back to academia, started teaching, started taking PhD students, started doing research. World War II broke, he again joined the army, the Polish army, fought against first the Nazis. The Nazis captured him, put him into jail, he got tortured. He was released by the Germans after the Soviets took over, and the Soviets put him back to jail again, where he got tortured. And then the Soviets released him. Well, he just brushed everything off and joined University of Warsaw and continued the same research which he had left before World War II. And this gentleman explained the entire phenomena of the difference between absorption and emission in these kinds of fluorescence material. The term fluorophore, all of these new descriptions have significant contribution by Professor Jablonski. He figured out, or he was able to explain in a proper manner, that why we are seeing this difference. A material absorbs light at a specific frequency, it emits light at a different frequency. There is always this difference between absorption and emission. Number 2, almost always, a majority of the time, the absorption happens at a higher frequency, at a higher energy. The emission, on the other hand, occurs at a lower frequency, a lower energy. There is a difference in the energy levels between absorption and emission. And why exactly this is happening? What exactly is going on internally in the atomic scale for material that shows this process of fluorescence? This entire process is called fluorescence, where certain material absorbs light and then emit light at a different frequency. It absorbs light at a higher frequency, it emits light at a lower frequency. This entire process is called fluorescence, and this gentleman Jablonski, Professor Jablonski, explained it using this very famous Jablonski diagram. No fluorescence topic is complete without fully understanding what Jablonski diagrams are. So, let us try to understand this. This forms the fundamental of any fluorescence studies, and you have to understand it. So, like I said previously, that for many molecular material, organic material, conjugated material, they have energy bands. The energy bands are actually quite thick, and each energy band contains this large number of orbitals joined together. They have sub bands in between, they have orbitals in between. So, the ground state itself contains not one but many. Similarly, the excited states also contain not one but many orbitals overlap to one another. They are very close in frequency among each other, they are very close in energy level among each other, but they are still distinct. They are similar but not same. Understand the difference between similarity and same. They are similar but not same. So, they are joined together. Whenever you send some amount of, so at the very beginning, let us start. At the very beginning, in the ground state, most of the electrons are occupying. Then you subject it to some kind of absorption. You send some amount of light, some amount of photon, and the electrons in the ground state moves up to the excited states. Electron absorbs this photon, electrons eat this photon and moves up to the excited state. There is no requirement that the electron will have to move to the first excited state. It can go to the second excited state, or it can go to further and further. But the fact of matter remains that these are pi bonding. Pi bonding have the delocalized molecules. These are actually carbon based or conjugated molecules. So, it might have higher energy levels S2, S3, S4, S5, but they are very unstable. The electrons can actually go to any other level, but the higher it goes, the higher energy level it goes, the unstabler it becomes, and it tends to return back to either the stable or the stablest or the moderately stable level, which happens to be S1. This is the stablest, S0. S1 is also moderately stable. S2, S3, S4 are incredibly unstable. Remember, the molecules are, I discussed in last class, the molecules in conjugated materials, they are strongly bound, but they are very weakly bound with respect to other molecules, van der Waals forces. So, if you supply more and more energy, they melt, organic compounds melt, they have low melting point. So, anyways, even if there is electron which goes to higher level S2, S3, S4, by internal conversion, it quickly falls to the nearest semi-stable mode, which happens to be the S1, which is to be the next excited. There are several excited states, it falls on to the nearest or the lowest excited state. And this happens in internal conversion, and this process, this entire process where electron goes to very high energy level and then drops back to the original or the first energy level, happens at a rate of 10 to the power minus 12 to 10 to the power minus 15 seconds, picosecond, attosecond, femtosecond scale. So, it is very difficult to look and actually measure it. After that, once it has fallen into the next excited level, the lowest excited level S1, it can move inside the S1 band. It can move, there are several different orbitals within the S1. It can move within this using internal conversion, which I told you, vibration, phononic vibration, or basically heat, and from there it jumps back to the original position, giving away a photon which we called as fluorescence. Now, understand the fundamental difference. Electronics engineers, when they talk about electrons jumping from valence band to conduction band, they do not care which part of conduction band or which part of valence band it is going from. In case of organic molecules, in case of molecular materials, which part of valence band or which part of conduction band is quite important there, because valence band, conduction bands are quite thick. They contain several different molecular levels, molecular orbitals, and it can jump from either stage 1 or stage 2 or stage 0 to all of these different stages. Now, electron moving inside a particular band does not require photon to be emitted. It is like, as I said, moving within room 1 to room 2 of ground floor, or room 1 to room 2 of first floor, or moving from lane 1 or lane 2 of a highway. It does not require much of an effort, and simply by shaking it off, simply by vibration, the electron can move. But if an electron needs to change the entire highway, if the electron needs to move to a different highway, or if the electron moves to go from first floor to second floor, it has to do some amount of hard work, and that is by emitting a photon, and that is done by the process of fluorescence. So, therefore, there is a mismatch, there is a gap, there is a difference. The photon that is absorbed takes it to a different level, the photon that is emitted comes from a different level, different sub level. Mark my word, different sub level of the same energy band, and this fluorescence happens at a rate of around 10 nanosecond, 10 into 10 to the power minus 9 second. And this process, this entire process where there is a mismatch between energy absorbed and energy emitted because of the internal conversion, because of having several different sub bands within a single band, is what is the reason of the gap between absorption and emission, and the entire process is fluorescence. There is another process, and that is phosphorescence. The fundamental difference, as I said, in phosphorescence and fluorescence, fluorescence is a fast process, it requires constant supply of energy. Phosphorescence, on the other hand, does not require a constant supply of energy. Why? Because, well, here it gets interesting, it gets little bit of quantum mechanics to come in. The energy band here, the S1 energy band, under certain circumstances can split. It is called spin orbital coupling. Do not worry, I will not discuss too much detail onto it, because this is not a quantum physics course, this is a biophotonics course, but understand this, spin orbital coupling happens. What does spin orbital coupling happens? It means that there are three different fundamental forces, or fundamental, let us use the term factors, affecting this energy level. There is this magnetic dipole, there is this spin of electrons, and then there is this electrostatic potential that can break one particular bond, one particular energy level into 2 or 3 different subbands. They can be at higher energy level, lower energy level, but splitting the energy bands can split under certain circumstances. The spin, last time, remember from previous class, you can rewind and go to previous lectures. Usually what happens, the electron here at ground state and the electron at S1 are paired, i.e., if the spin of electron at ground state is up, the spin at excited state is down, and these two are paired with one another. Even if the electron returns back to the original position, they are anti-parallel to one another. And according to Pauli's exclusion principle, this is accepted two electrons can stay in the same molecular orbital with antiparallel spins. Well, however, due to inter-system crossing, maybe some kind of vibration, maybe energy split, what happens is that when electron moves from this level to this level, its spin reverses. So, now at the excited triplet state, the spin is this, at the ground state, the spin is this. When the excited state molecule returns to the original state, it is violating the spin rule. And this is not accepted. Since this is not accepted, basically the electron is disallowed from returning home. Unless it changes its behavior, it is not welcome back in home, and it takes huge amount of time to change and return back to the original case. Because of that, you have sent energy, this has absorbed energy, it has returned back, but since its spin has been turned upside down, it is having difficulty returning back. It takes all those time to emit energy, somehow shake, vibrate, emit energy, whatever it can, to return back to ground state. This is a fast process, this is a slow process. This is fluorescence, this is phosphorescence. Hence, you see your radium clocks, radium watches glowing at night, because they have been excited by light in the daytime and they are emitting light for a long period of time with a very feeble, the brightness is much less as compared to the fluorescence. Comparatively, part by part, one electron produces less amount, high energy of photon in fluorescence as compared to phosphorescence. So, this is the highest, the absorbed photon, then come the fluorescence photon, that energy is slightly less, and phosphorescence is even less, of the same type of material if possible. However, in real life you also see the same material giving you a combination of fluorescence and phosphorescence, that is also there. So, the fundamental thing you have to understand here, that emission spectra are typically independent of excitation wavelength. What does that mean? Meaning, as long as this hurdle between S0 to S1 is over, you will get a fluorescence, because no matter what energy have you submitted or what energy you have supplied, if you are not breaking the system, if you are not completely destroying the system, it does not matter if it has gone to S2, S3 or S4, because from S2 to S1 or S3 to S1 or S100 to S1 is very rapid, very fast, because these are incredibly unstable energy levels. Electron does not like to stay there at all. As soon as electron gets there, if it can, without destroying the system, if it can, it returns back at a femtosecond level. And then once it has a breathing space, once it can breathe, it can come back to S1, a semi-stable level, it within some amount of nanosecond emit the light. So, as long as you have covered the distance, the minimum distance, the threshold distance of S0 to S1, the ground state to fast excited state, it does not matter, it is independent of the excitation wavelength. So, this energy, this absorption energy, as long as it is above this threshold, does not matter, you will keep seeing the same fluorescence, because transition from S2 to S1, S3 to S1 does not cause fluorescence. They are highly unstable, electron can simply shake and jump back to the next level. Okay. Now, Stokes gave reason for this mirror image rule. Sometimes it is used, sometimes it is also not used, but what it actually means is that because of the Frank-Condon principle that we discussed last time, since the nucleus are much heavier, and remember the previous lecture, nucleus takes huge amount of time to move, electrons can jump at a very smaller period of time. The energy level, the subband splitting, the subband arrangement of energy level at higher, the nearest excited level, and that of the ground states are mirror image to one another. It is assumed, it is expected, and although it's a rule, it states that the way this has moved up from 0 level to second level, from 0 level to first level, from 0 level to 0 level, it can return back similarly in a similar fashion. So, moral of the story, what it says is that the shape of the spectra in the absorption will be the shape of the spectra in emission. There will be a gap, there is going to be a gap because the electron that has moved here has come this side and then, but there is going to be a mirror symmetry, a symmetrical image between emission and absorption. The mirror image rule is several times violated. It is not always the case that the arrangement of energy levels at this case and this case will be same. Well, the reason for this is they say that the arrangement of this sub-level, sub-molecular, these molecular orbitals in an energy band is mostly due to the boundary condition put by nucleus. And even if you have excited the electron, since the nucleus is not moving per se according to Frank-Condon principle at a rapid rate, the energy, the configuration of the energy level is also not changing. Remember Frank-Condon principle I said previously. So, there is a mirror image taking place, although there is regular exceptions that we see to that. So, several other factors that you need to understand when it comes to fluorescence. First is quantum yield and lifetime. Quantum yield basically tell you that the number of emitted photons with respect to number of absorbed photons. So, it is basically a term for efficiency, yield, how much photon you have absorbed and how much photon you have emitted. So, this is the formula. Gamma is the emissivity or emittive rate and KNR is the non-radiative radiation. This is the amount of photon, this is the electrons shaking and coming from higher energy level to lower energy level by phonon or vibration or just by shaking themselves. So, how much of non-radiative transition has happened and how much of gamma, i.e. photon, has come up. Obviously, at the best case this non-radiative transition is almost 0. We actually see this in laser. Remember, in laser, if you know a little bit background of laser, don't worry if you don't know, I will be discussing about laser anyways. The same photon that is doing the spontaneous emission is being reflected. So, it is amplifying. So, there is no difference in photon energy in a laser, but this is not laser, this is organic compounds, this is fluorescence or fluorescent materials or also known as fluorophores. So, this is the formula. There is always a term which is the non-radiative emission and that reduces overall the quantum yield. There is also lifetime, the time available for the fluorophore to interact, how much time the emission photon will be available, and that is given by this particular formula. These are some of the factors that you need to know. These are very, very self-intuitive. Just reading it, you will be able to understand. Quenching. Quenching is an important phenomenon in fluorescence. So, nothing is perfect. Life is of course not perfect. You will not have a fluorophore just by itself. You usually have a fluorophore, a fluorescent material in an environment where it is surrounded by several other molecules, several other materials, right? Like in a solution. Like in a solution, you have different type like quinine water present, quinine present in water, like rhodamine dye present in some kind of a methylene blue, or these kinds of dye present in some kind of solution. So, the fluorescence intensity can be decreased when the fluorophore, the material which is emitting this light, that molecule, that fluorophore, that substance is interacting with another substance, is interacting with another molecule which is not at all fluorophore, right. A fluorophore molecule in a solution is interacting with a separate molecule which can be organic, which cannot be inorganic, and they can collide, thereby simply collision will let the electron fall without any kind of energy emission. It can also happen that fluorophore makes a compound with this other element, makes a compound with this other material, and thereby the entire molecular orbital things, the energy levels changes, because it is no longer fluorophore. It has converted itself, it has formed a compound which is a non-full fluorescent complex. Okay. And some of the typical examples of quencher, something that attacks or changes or modifies these fluorophores, are something common as oxygen, halogen and amines. But remember, there is certain examples or utilization of the quenching process. These days with the coronavirus pandemic, you know about oximeter, right? Pulse oximeter, you are putting it in your finger and you are measuring how much your blood has oxygen level. If it is below 80, you should go and see the doctor immediately, they say. Think about that. This is not the same thing, but think about that. If I have a solution, blood say, and I have put some amount of fluorophore, the fluorophore is emitting light, and I am constantly supplying oxygen into it. With the amount of quenching, less and less amount of light is getting emitted from the fluorescence. Can I make a measurement, an optimization of how much oxygen this molecule is having, this molecule is retaining? Can I think in that particular direction? Do you think the pulse oximeter uses fluorescence? Think about it. Fluorescence anisotropy is a very important topic. So, fluorophores try to absorb, they have a preference for absorbing light which has the electric field anti-parallel or electric field vector in the direction of their dipole moment. So, if you have made some kind of a polarized light, if you have sent some kind of polarized light that have put all those fluorophores in a solution in a particular direction, you will see a polarized emission. Most amount of light is being absorbed and most amount of light is being emitted. After some time, obviously, when the polarization removes, the distribution of the fluorophores become randomized. That also start reducing your emission. This is called rotational diffusion. You can therefore think about the time frame it requires for your fluorophore to get aligned and to disalign, how much time it requires. We require all of these information when we are looking for, say, protein studies. We need to see how proteins are interacting with one another. Are all the proteins in similar direction or they are randomly oriented? What about DNA? What about the DNA base pairs? Are they all aligned together or they are disaligned together? So, another important thing which we are going to discuss in the bioimaging part is the resonance energy transfer. I think medical students have had learned about this quite a lot, that is Foerster resonance energy transfer or fluorescence energy resonance transfer. It happens when there are two molecules, one is emitter which we call as donor and one is acceptor. The emission spectra of this matches with the absorption spectra of this, right? Two molecules, this molecule emits a particular photon, the emission of this photon matches with the absorption of that specific molecule, right? Two separate molecules, the emission spectra of this molecule matches with the absorption of another molecule. So, that is called donor and acceptor. However, here you need to be sure that it does not involve necessarily emission of light by the donor. It is also not emission of donor absorbed by acceptor. It simply tells you about the distance between donor and acceptor, meaning if molecule A and molecule B's emission matches absorption of molecule B. Unless they are close to one another, unless there is a physical interaction between them, this process does not occur. So, even in the solution there are molecule A and B, if they are not close enough, this resonance energy transfer will not happen. This is the shaded area where the energy transfer can take place, because this is two separate molecules, acceptor's absorption and donor's emission are near about overlapping, and this process can only happen when absorption and emission molecules, acceptor and donor molecules, are physically close to one another. If they are quite separate from one another, even in the same environment, even in the same solution, it does not take place. Thereby, we understand inside a cell how close a particular organelle is with, say, another protein, how close a pathogen is with respect to a cell or with respect to a nucleus or somewhere else, or how close protein A is with protein B. If they are closer together, they will make some kind of a complex which we need to think about. So, we will be discussing FRET quite in a bit more detail in subsequent classes. For the time being, I just gave you a hint of what this is. So, now coming back to our original thing, why do you use this marker? Why do you use this marker? You use this marker to highlight a specific of a certain passage. You have a big page, several lines are written here. One particular line, one particular paragraph is important, and you have therefore marked it with a marker, right? The same thing happens in microscopy. You want to understand, say for example, how the nucleus of a specific cell is behaving. You therefore use a fluorophore, a very, very small fluorophore. That fluorophore get tagged, get attached to the nucleus. Chemically, we can make certain materials attached to another organic material. So, this fluorophore attaches to the nucleus or any other specific part, and then you are shining light. You are shining a specific light which this fluorophore tagged to it absorbs, or let me use this term. This fluorophore is attached to my hand, and this fluorophore absorbs yellow light. Whenever some other light, it does not absorb yellow light, it emits yellow light. Say it absorbs blue light and emit yellow light, and with this, whenever you put it under microscope, whenever you see a yellow emission coming up, you will understand that is coming from the area of the nucleus region. Thereby, you can identify this very beautiful inside the cell, even to a single cellular, single molecular level. This is the fluorescence microscopy. This has revolutionized biology. You simply have a specimen, there is a light source, excitation filter filters out the blue light, the high wavelength light. This the material absorbs. The material then emits another different frequency. This different frequency is quite different from the illuminating light. Obviously, there is a gap. We have utilized this difference, and we have used a filter that can only filter out the emitting light. This is not difficult in normal stereo zoom microscope. Here we are only filtering out the emitted light, and thereby you see this beautiful microphage, where more than these days we use multiple fluorophores. One absorbs blue light, gives green light, one absorbs green light, give red light, etc., and thereby you get a good, beautiful picture such as this. Okay. Very quickly, I will tell you two separate measurements in fluorescence microscopy. One is steady state, one is time resolved. Steady state is under constant illumination. The light source is constantly on and you are measuring it, and then there come time resolved, where the light source sends pulses. It is usually laser and it pulses. It is a dynamic measurement. Every time you send light, you get an image. There is a gap, then you send light, get another image, and you match these two images, and you see how the cell is a living material, what is the dynamic processes, how it is slowly changing. It's like animation, one picture after another picture after another picture, and you merge it all together, and you see how the cell has moved, what kind of chemical reaction had happened. So, this single-handedly revolutionized life sciences completely. Now, we are able to observe by fluorescence microscopy single molecular level changes happening inside a cellular environment. Application in life science, see how beautiful this has happened. Sendai virus, this is murine respirovirus that these days is called. This mostly affect rodents, not helps humans, and they are trying to see how the infection rate have changed from 0 hours to 24 hours. The blue part are the antibodies that this Sendai virus generates, and the green part is either cell or the cellular material. So, they wanted to see what happens, how exactly the virus replicates, how exactly the virus changes from 0 hours to 24 hours in two different cells. One is a lung cancer cells, one is a colorectal carcinoma in rodents, and all of these static as well as dynamic measurements can be done from 0 hours to 24 hours at a difference of say 5 minutes, 10 minutes, 15 minutes. You can have all these pictures and you can see the rate of infection, how the virus is spreading. Can it be used for detection of coronavirus in human nasopharyngeal or oropharyngeal swab? Can we utilize this kind of technique to image and understand the spread of coronavirus? What do you think? Anyways, that brings us to the end of this particular chapter as well as module number 2, which was the very basic of light matter interaction. We discussed about fluorescence and phosphorescence, Jablonski diagram, quenching. Just go through it. The significant book that I have used to prepare this lecture is Principles of Fluorescence Spectroscopy by Professor Lakovich. This is one of the best books on fluorescence microscopy. If you are interested to know more about fluorescence microscopy, read this. If you are more interested in quantum mechanics, I am not talking more about quantum mechanics. You might think it is hand waving, but remember, quantum mechanics is a vast field in itself. So, some of you who are interested to know why the energy splits, why basically singlet states come to triplet states, why the spin moves, I urge you to check for those. And if there is enough demand for me to teach you, take a separate section just for quantum mechanics, maybe that will be done, but for the time being I would like to focus on biophotonics, which is the main theme of the course after all. So, next class I will be teaching you biology. Thank you very much.